Hi guys. In this video we're going to take a look at Pascal's law. Pascal was a Frenchman, one of the first people to do research into fluids and pressure and things like that. And he discovered something kind of interesting. He discovered that you can use an incompressible fluid like water to act as a force multiplier. In other words, if you apply a small force right here, you get a larger force coming out over here. How does that work? Right? Because that's a very useful thing. Where we usually use this today is in any kind of hydraulics, whether it's a mobile hydraulic like a backhoe or a stationary hydraulic. You take your car to get the oil change, they put it and they jack it up. They're using Pascal's law, right, to lift your car. Um, so what's happening? How do you multiply force, and what's the cost involved? Because nothing comes for free. There has to be some cost associated with multiplying this force. Well, here's what's happening. You'll notice that we have a small force here, but we have that force acting on a relatively small area, A1, which represents the surface area of this green piston on the left side. We have a larger force F2 associated with a larger area, A2, the surface area of this green piston on the right side. Now here's what we know. The pressure at this point right here has to be equal to the pressure at this point right here. And that's because of what we learned in the previous section on the variation of pressure with depth. At a given depth, it doesn't matter what the shape of your container is, as long as you're, well, I think under any circumstance, at a given depth, the pressure has to be equal everywhere, right? And so since these two containers are connected, the pressure is going to be the same at both spots here because these pistons are both at the same position. Now, what happens? Well, we exert a small force here. That pressure gets transmitted through this connection to the fluid over here where the pressure gets exerted. But once we get over to the right side, this pressure is exerted over a larger area. What that means is there's going to be a larger force. So the name of the game is pretty easy. You set your car on top of this piston, you exert some kind of a force on this piston, and you can lift something that you normally wouldn't be able to. Okay, here's how you cost that though. Here's where how you pay for it. If you push this piston down, let's say 6 inches, you've displaced a certain amount of fluid. Well, this is a much larger surface area, right? The volume of fluid associated with 6 inches over here might only be associated with the rise of 2 inches on this side. In other words, you had to push further. You had to displace this piston further, and this piston displaced less. That's the price. If you want to raise your car up 1 foot, you can do it, but you've got to displace this down more than 1 foot. So in principle, there is no limit to how many times you can multiply the force, as long as there's also no limit to how far you can displace this piston. Now, there's also the matter of what happens if I create so much pressure that I actually burst this container. Yeah, perhaps under some circumstances that's an issue, but most of the time that's not the hard problem to solve. So Pascal's law allows us to multiply force at the cost of displacement. Now, you could do this the other way around. You could turn these arrows around so that this one's pointing down and this one's pointing up and say, I'm going to exert a larger force on this larger area and I'm going to get a smaller force on a smaller area. You say, why would I ever do that? Well, I'll show you an example in a minute, but what you get from that is a larger displacement. So in Pascal's law, there's always this trade-off between force and displacement. If you want to multiply force, you have to pay with extra displacement. If you want displacement, you pay for it with extra force. Let's take a couple examples here. Here's a first example where we're going to exert larger force, but in return, we're going to get a more significant displacement. This could be a syringe. In this case, I don't have a syringe. I've got some weatherproofing, a silicone caulk here. But the idea is that you've got a large surface area down here, and you've got a very small, much smaller surface area up here at the tip. So let's go back to our picture. Large surface areas associated with large force, small surface areas associated with small force. So in this bottle of weatherproofing silicone, we're going to have a large force that we have to exert down here. Well, you already know that. If you don't, go to the store, get some caulk, or go find some in the garage or the shop, and just try to push on the end of it with your thumb or something like that, or a stick. It's really, really hard. For that reason, because you need such a large force on this end, we buy a caulk gun and we put the bottle of silicone weatherproofing into it, and you squeeze the handle a few times, and that generates the force for you. Out this side, we have a very small force, but what we do get is a large displacement. We get a lot of our silicon coming out here, right? And the exact same thing happens with a syringe. If you're getting your flu shot, all the vaccine that's in the syringe doesn't take much. You got to push on it, right? The nurse administering the shot has to push on it, but you're getting a lot of flow through that very, very tiny syringe needle. So this is an example of almost using Pascal's law in reverse, where you apply a larger force, but you get a greater displacement for it. Here's an example of applying a small force and using Pascal's law to magnify that force. These are the brakes in your car. Now, there's a couple of things going on here. First of all, you're applying this 100 newtons of force to the brake pedal, but this is acting like a lever arm right here. And we learned in chapter 11 that torque involves a force, but it also involves a lever arm. And making the lever arm longer magnifies the force. That is not Pascal's law. That's torque. So going from this force your foot applies to the brake to this force that's being applied to this cylinder right here is torque. That's not Pascal's law. Here's where Pascal's law comes in. This cylinder is connected by a pipe filled with brake fluid to two cylinders. These are called slave cylinders. This is called the master cylinder. The idea is that these cylinders on the brakes are going to respond to what you're doing with this cylinder when you pump the brakes. Now you've got to have fluid in there. This doesn't work with air. And if your brake fluid's low, you'll feel your brakes are kind of spongy because the air is too compressible. This whole business with Pascal's law really only works with incompressible fluids. So this force right here is applied over a small area. The pressure, of course, has to be transmitted because it's all connected by hosing to these slave cylinders here. The slave cylinders are acting over a larger surface area right here and right here. You can tell that's much larger than the area right here. And that's going to multiply the force that's exerted when your brake pads squeeze these brake rotors, right? And in principle, that's how all brakes work. The details of it might vary from vehicle to vehicle, but that's the idea. It's also the reason you want to make sure that your brakes have plenty of fluid in them so that the system actually works. So that's Pascal's law and a couple examples of how Pascal's law is applied.